So welcome everyone. I'm Sama from TU Dresden, and I want to talk about Attested TLS, the design space that we have for this specific line of protocol, the trade-offs that these protocols actually make, and then finally I will talk a little bit about the standardization efforts which are ongoing for Attested TLS. I want to take a moment to thank my travel sponsors, GenXT and Pacific Analytics, who have helped me being here. Thanks a lot. And why I am in the confidential computing track, the main idea is that there is no confidential computing without remote attestation. It's a pity that I actually have to put it on my slide. The reason is that Confidential Computing Consortium in the very beginning did not have this in their definition, and we believe that it's really a main thing without which you cannot have confidential computing at all. Anyway, we managed to convince them, and it's now in the new definition of confidential computing already. So just as a reminder of why I am here for confidential computing track. But there is a problem in remote attestation, and I want to also acknowledge that there is a lot of terminology gap between different organizations, providers, and so on, and also even in the internet drafts. And the way I'm going to view remote attestation is really the mechanisms for communicating the remote evidence. And the idea here is that it has some problems, namely privacy concerns, that the claims which are, by claims I mean anything that is transmitted or anything that the attester is trying to transmit to the verifying underlying party, which is a combination of verifier and underlying party according to RFC 9334. These claims are visible to the adversaries, and these claims contain the hardware level information, which means that the adversary can now get information to that, and if there is a weakness in the hardware, if there is a weakness in the firmware and so on, it can utilize these claims in order to benefit and better attack the system. Also, there is a problem from security perspective, namely you can have relay attacks, and this figure is going to show what that actually means, because the confusion is also that whether it's a relay or replay and so on. So the thing is that the verifying underlying party will send over a nonce to get the attestation for this attester. This attester, which is malicious, can actually forward it to some genuine trusted execution environment, get back its evidence, and then pretend that it's its own evidence. That's how that attester will actually manage to convince the verifying underlying party that it is in genuine state, it is in desired state what it was expecting, but in reality it is not, because the evidence comes from a genuine TEE, which is completely different entity from the attester. However, it convinces the verifying underlying party that it is correct. What we need to do then in order to solve both of these problems is that to communicate via TLS, one of the most, or any secure channel, TLS being one of the most famous ones and most securely analyzed protocols. And what happens here is shown on the left side. That's the certification authority is the root of trust, or the trust anchor, which is initiating all of that. And the idea is that basically the server will send over a CSR asking for a certificate signing request. It will issue, the CA will issue that certificate, and with which it will do the TLS communication in order to secure the communication between the two entities. That is namely the client and server in case of TLS. And on the right, we have the remote attestation, which is saying that the hardware is itself the root of trust or the trust anchor, and communicating with the attester. The verifying underlying party will have some interaction protocol, which is namely the can be the nonce-based protocol. And you see a kind of analogy between the two, which is at the bottom of the slide. The certificate and the evidence both are signed by different keys, one coming from the certification authority that is from on the left side, and the other one coming from the attestation key, which is from the hardware manufacturer. So both actually have complementary characteristics, namely the hardware is guaranteeing what software is running on top of that hardware, and the certification authority is guaranteeing that what is who is the owner of that specific machine, who is in ownership or control of that specific machine. We believe that both characteristics are complementary and that's not overlapping, and thus we need to retain both properties in order to get strong security guarantees. And a short way to putting it is that TLS is giving you something about, some guarantees about the identity of the machine. And on the right, that the software stack, that's basically remote attestation, is giving you guarantees about what's running in the software or the workload. That is the measurements. So with both TLS and attestation, we need to combine them both. That's what I just motivated. And the idea of combining them both is now the design space, in which ways I can combine them. The most important characteristics of remote attestation is the signature. And cryptographically, it's important at what point in time I am actually doing the signature relative to the handshake, that is the TLS handshake. Either I can do it before, in between, or at the end of the TLS protocol. That's what we name as pre-handshake attestation, intra-handshake attestation, and post-handshake attestation. And these basic patterns can also be combined, which is what I'm saying at the last, which is the combination of basic designs are also possible, which could be, I could have pre-handshake attestation in order to establish the secure channel, and I could do a round of post-handshake attestation in order to check the post-handshake claims or the integrity of these claims. Right, so we have seen like 3 different forms. I want to go more concrete about this. In the table columns, you see RATLS, which is a proposal by Intel, a TLS attest, which is a proposal in the IETF TLS working group, and the final one is SCONE, which is one of the solutions proposed in academic paper and is also in production. So the kind of criteria that I have here is inspired by the EAL levels which are there. And what it says is, do we have open source implementation? First point. Second point, do we have informal specifications available? Implementation and informal specifications are 2 different things. Implementation just means that there is some piece of code which is available in order to do something. But specification actually specifies what that thing is in reality. What does? What are the cryptographic steps? What is it doing in reality? The real specification. For one specification, there could be multiple possible implementations and multiple different ways of doing that. And the specification specifies what exactly it is doing cryptographically. Then we have formal specifications. Converting that informal specifications to formal is also another step which adds more granularity and precision to that specification. And based on these specifications, now one can do a formal analysis, which means that whether it upholds the guarantees that were supposed to be taken from that system. And the final step is somewhat related to this, but a little bit different, which is saying not of the specifications, but of the implementation. That is going back to the implementation in step 1, which is that I developed some piece of code. Does it actually preserve the properties that I was required to uphold? So I want to emphasize 2 things, namely that open source is a must for confidential computing. It doesn't really work without that. If you have a verifier, for instance, which is not known to you, which is doing something fuzzy and it's not clear what it is doing, I don't believe that can be qualified as confidential computing at all. That may very much be security through obscurity and formal analysis, which is a concrete requirement now at the TLS working group for standardization. So I will now talk about 2 specific schemes inside that which I described, namely the intra-handshake and the post-handshake scheme. First, I will describe about intra-handshake, the internet draft for SATI TLS attestation, which is one of the colleagues from Lenaro and others have actually proposed that. And what it actually does is some of the concerns about from formal analysis, of course, one is looking for attacks and the possibilities of different problems inside the attack. So this is by no means meant to be saying that this is actually wrong and the whole draft. So what we are trying to say is that from our analysis, what we have figured out the problems that we are trying to highlight. First of all, this is talking about remote attestation only, and it's unclear what is really the benefit of remote attestation only, in the sense that what would an end user gain from this? If it gets an evidence, which is for the cloud.example.com, which it wanted to connect to, and it gets only an evidence that this has this measurements XYZ, and it has no guarantee that it is really connecting to cloud.example.com, the problem then would be that it could be any random dictatorship. It could not be necessarily cloud.example.com. It could be anything else, and it could go over to anywhere in the world because there is no PKI certification. There is only this evidence which is guaranteeing that still it is within the TEE, but there are a number of assumptions which the TEE makes. The security model says that there are no side channel tags, there are no this, blah, blah, blah. So even if one of those assumptions is broken, then everything is broken. And this really leads to the problem, which is namely, using this protocol, the security breaks if there is only one single compromised machine, not only in that specific data center, but anywhere in the world. Even if you manage to break one single machine, you can divert all connections to that specific machine, and then everything is then broken. So that's really the problem with remote attestation only, that it is not providing the security guarantees that are really required from such kind of solutions. And the assumption that we make here is that until it has been added to the revocation list, and we have seen from SGX, for instance, like that was available on Twitter, that the keys were available on Twitter, and for several months it was open for anyone to sign anything that you want. And that's really the problem that needs to be solved, and we believe that one way of solving that is to provide you guarantee via the certification authority that this specific machine is running that specific software, which is a complementary guarantee, and it strongly enhances the security of the whole system with the fact that I don't have to break any single machine in the world. I, as an adversary, have to break that specific machine for which the certification authority is saying that this machine is owned by this specific entity, which strongly limits over the capability of the attacker to very small subset, namely not anywhere in the world, in that specific location which the third party is claiming that it is located, that is the certification authority. And secondly, that it has all the guarantees of the trusted execution environment provided by the hardware manufacturer. So we believe combining both certification authority and the hardware manufacturer provides a very strong level of guarantee which is required from such systems, for example, in the financial domain, for example, in health domain, and so on. But there is a challenge in order to do that, which is namely that the certificate verify message of TLS is not extensible. And we have proposed at least 3 solutions shortened down here, so there are others as well, within the intra-handshake how to solve this problem, which is that we can modify a certificate verify message of TLS in order to provide proof of possession of both. We can provide multiple certificate verify messages, and number 3, we can have a channel binder which binds both these mechanisms together in order to stay still connected to the certification authority-based guarantees. So I have here a lot of text I will try to summarize, and this is a work in progress that we are currently doing. Intra-handshake attestation has its own inherent limitations. Number 1 is the complexity which comes inside this. Although it has the benefit that it provides you out of the box a connectivity, remote attestation along with TLS, you as an application developer do not need to care about what to do with all this kind of security, do not indulge with all of these things for your specific application. But at the same time, it has the limitation, namely the complexity, that the TLS protocol, when we are messing around with the key schedule and all that kind of nitty-gritty details of the TLS, it's really dangerous, and it needs formal guarantees to be provided. Secondly, in the internet draft, it's claimed that it provides freshness, but in reality, that's a bit tricky. Intra-handshake, as on the slide I was showing, like signing happening at what point in time with respect to that. So the very first thing is that basically it's providing only the claims which are, actually the time, so the very first is the time. Temporally, when you are establishing the connection, it's temporarily giving you guarantees only at that point in time. There is no freshness guarantee afterwards. What happens afterwards is completely out of scope. Secondly, there are a number of claims like runtime measurements which may not be available at the time of establishment of that secure channel. And that means basically all of these claims are ignored by such a connection. So that's what I have as the next point, which is the runtime measurements, because the load time measurements will remain constant. The runtime measurements will keep changing. And how do we take care of these runtime measurements? What application is running? What OS is running? How do we take care of these? It seems from this analysis that post-handshake attestation is an absolute must for such kind of use cases at least, that we still need to take care of all the post-handshake. And then it may be a choice between pre and intra, that which one we use for establishing that secure channel, and still use post-handshake as a post-handshake integrity. So I then want to go about with the post-handshake attestation. Namely, the proposal here is to use RFC 9261 exported authenticators in TLS. And what it says is that it allows you to do post-handshake attestation using these authenticator requests and authenticator coming from the tester. You send a nonce as part of your authenticator request as a client certificate request message, which is essentially the same as the certificate request which is sent by the server in the typical TLS, the standard TLS. And the authenticator will consist of certificate, certificate verify, and finish messages. And the certificate message will contain that specific evidence. So we do not change any TLS thing out of the box. Basically, this is going to provide you all guarantees that at this point in time, after the handshake, what is the real status of that specific machine. So yeah, so this is one of the proposals that's in the initial stages. We are hoping that at least we will make some progress on this, because as I said in our analysis, it turns out that post-handshake attestation is an absolute must, which is still required. Which one we choose for establishing a connection, whether pre or intra, is then a question between the two. However, both of these drafts in particular and in general, the post and intra handshake have some problems. Namely, how do we provision these keys? How does it all bootstrap? In original path, things will happen like this. On the left, there is the client from TLS perspective, and verifying relying party from remote attestation perspective. On the right, you see a CSP, which is running all of that workload, confidential computing workload inside the VM. And in a typical flow, there will be that they will establish a TLS connection based on this. And step one is showing that it sends over a request. Step two is showing that it's basically quoting agent in specifically, like in SGX, that would be quoting enclave. That will generate an evidence, send over back to the VM, and the VM will send over back to the verifying relying party, which will accept the evidence because it has the right measurements which it expected, and the right and the key which it trusts or it has in its trust store. However, the problem is that there can be a diversion attack, because CSP inside the confidential computing threat model, at least the one that exists at the moment, CSP is considered out of the TCB. And how that actually could, what could actually happen is something like this, that the CSP could divert it to a compromised machine that it has secretly compromised. It's not yet revocated. And under this condition, what can happen is that everything that I have shown exactly, it can do like this. And it can show the measurements of M1, which the relying party was expecting, and sign it with the key which it has already compromised. And with this key, which is already there in the trust store of the verifying relying party, it can convince the verifying relying party that it is correct. And then it will basically impersonate the original VM that we wanted to have and steal all the secrets from the TLS client. Exactly same thing happens in the case of trustee. The only difference is that switch of roles. Instead of the TLS client, we have the TLS server. The client is now on that other side, which is in the CSP. And the same attack can still be applied to the trustee thing. And one open question which we have still open is, how does this certificate which is shown in the encrypted workload get into that workload in the first place? And that might be a part of the workload itself, but then important question here is, who owns that private part of the key which is within the certificate? If somebody has sent over this certificate or put it into that specific workload, it means that somebody has actually generated that private key corresponding to that public key. And who is that specific entity is still unclear in this threat model, that who is generating that key and how is that entity going to be trusted. Because if somebody owns you a key, somebody owns your key and sends it over to you, it means that there is not only you who is owning that key, there is somebody else who has actually generated it in the first place. And you absolutely have to trust that entity, because that's the one who has the power to actually pretend to be you. So what we are then investigating currently is that is the the claim for confidential computing that the CSP is completely out of the TCB, is it really realistic? Or in other words, how realistic is that claim? And we came up with a bunch of criteria which actually deny this being out of the TCB. The first one being availability. We need things to move around. This cannot happen without availability. Nothing can move around if you don't have the availability of the software. So if there is no availability from the cloud provider, you cannot do anything. You cannot do any workload. You cannot run any workload, get any results back from that cloud provider. Machine identifier. There are regulations like data sovereignty regulations, which have host affinity, which is that machine which is actually running your workload. And this is not possible unless we trust that specific entity or trust some certification authority which actually guarantees me that this is that host which is running that trusted workload. Third one, location. Similar to data sovereignty regulations, there are now data residency regulations, which are coming from the fact that different countries do not trust other countries. That could be due to geopolitical tensions, and we are seeing many different examples of such things going on. And the reason is that if you have some workload which is running in your country which you do not trust, they could have the power to actually break that trusted execution environment and get over your secrets. And that's what they try to avoid by doing this, by limiting the location to only that specific region. For instance, the EU regulations, which are limiting the health medical data to remain within the EU, or for instance, German law, which is requiring the e-health data to remain within the Germany region. And such like threat model is going to violate all these conditions. In the bottom, I have 3 different criteria, which is that any of the boot software which is measured by which is not open source and is not independently reproducible is also one criteria. And then early boot measurements done by the VTPM. VTPM is typically outside of the confidential VM. For instance, in AWS and Google, as you see in the table, that's outside of that. So any measurement which is done by that is absolutely useless because you are trusting that CSP in order to provide you guarantee for that. So that's basically, in other words, your adversary who is measuring for you. And even in remote attestation, there is a hold of CSPs, which is absolutely concerning. So the next steps are to have a realistic threat model, which can be genuinely proven to be correct, and then a thorough comparison of both of the mechanisms that I have shown. And there are a number of pointers which you are very welcome to explore further for this. And the call to action, I would like to say that we would like your review on the drafts, the internet drafts that we have, and contribute to the formal analysis or give some form of review. You don't necessarily need to code, but you can give some review for that. And participate in the discussion. We have online meetings every Monday at 10 a.m. You're very welcome to that, and you can write to me your questions as well, some of the references, and I really want to acknowledge all the people who have contributed in this work. On the left, there are the co-authors or the co-editors who have worked with me in all of this work, which I presented. And on the right are people who have actually actively given us feedback on the different works that we have already done over the years. Yeah, with that, I would like to thank my sponsors again, and I'm happy to take any questions or comments or any feedback that you might have.
So if there are some properties that have to be attested by the party that's running these confidential VMs, doesn't that essentially mean that the vision of confidential computing is impossible because you must rely on the person operating the hardware, then what use is the rest of confidential computing's guarantees?
Right. I think the question comes back to this threat model, which we are currently investigating. Right. I believe that is so. A large part of this is basically theoretical marketing stuff. So I think what a good answer to that will lie in some of the research that we will follow on with the realistic threat model. And unfortunately, I do not have a good answer for this at this moment, but we are actively talking to the Confidential Computing Consortium, especially in the attestation SIG. We had some discussions over the threat model, and with the TAC, we need to follow up again on this in order to find something realistic what this actually means. I mean, both the chip providers as well as the cloud providers benefit from this claim that, hey, we are out of the TCB. Chip providers get to sell their chips. The cloud providers get to sell at a higher cost because now this is confidential in some sense. But what is the real reality is something that needs to be explored. So,
Thank you.
okay, then thank you very much. And I do have some follow-up questions on the slides, which I would like to follow up later on. Thanks a lot.